All right, so chapter 6 is talking about the normal distribution, and then test 3 in general is the normal distribution, and then we're going to talk about sampling distributions. So we talked about sampling in test 1, where we can't like ask every single person the problem, so we just look at a little sample. And then the normal distribution, like we talked about a second ago on test 1, we talked about left skewed, right skewed, and then normal meant that it was symmetric. So these are going to be normal curves, so they're going to be nice and pretty and symmetric, and we're going to use that symmetry to our advantage. So the standard normal distribution is continuous probability. Remember, continuous means that it's going to be over an interval. So like from this number to this number. Probability distributions have two characteristics. The probabilities is that X assumes a range of values in any interval lies within 0 and 1, including 0 and 1. Again, we're talking about continuous, or we're talking about an interval. So notice this time it says a range of values. Let me use a different color. So the probability that X assumes a range of values. So this is kind of like taking it a step further from last test, because last test we talked about a single value. Last test we talked about discrete probability. Now we're talking about continuous probability. So last test was a single value, discrete, and now we're talking about a range. Now we're talking about a range. We're talking about continuous probability distributions. Same thing, probabilities between 0 and 1, so nothing's different there. And the total probability of all mutually exclusive intervals within which X can assume value is 1. So same thing, if you add up all the probabilities, our probability is going to be 1 because that includes everything. So the same characteristics, just kind of relating it to intervals this time. Notice it says mutually exclusive. So mutually exclusive means so there's no overlap. So no overlapping intervals. No overlapping intervals. Mutually exclusive, remember, means that they cannot happen at the same time. So in total, with no overlap, it's going to equal 1. So differences in the probability distributions of discrete random variables from test 2 and continuous random variables to test 3, which is this material. So some differences. Discrete random variables have accountable values, where continuous random variables are not countable. They're intervals, so just the difference between discrete and continuous in general. Next difference is the probability distribution of a discrete random variable assigns probabilities to points, while this time continuous random variables assign probabilities to intervals. So we're still talking about intervals versus points, discrete versus continuous. And then here is kind of like the big difference. The probability that a continuous random variable X assumes a value within a certain interval is given by the area under the curve. The area under the curve between the two limits of the interval. For a discrete random variable, the value is given by the summation of values. So that's what we talked about last test. We looked at the different probabilities and then we added them up to find like the total probabilities. Now we're going to have an interval. So we're going to look at the area under the curve. I know some of you too have taken pre-cal and calculus. If you've taken pre-cal and calculus, it's the same thing. Or if you're planning to take pre-cal and calculus, we're looking at area under the curve. So it's the same concept. Where discrete is, let me put here, continuous is the area under the curve, where discrete is talking about the summation of values. So we're talking about area under the curve. What curve are we talking about? So here's this normal distribution, this normal curve, bell-shaped curve. So a normal distribution, which is also called a normal curve, a bell curve, or a Gaussian distribution, which this is just some famous mathematician. think it's high school mathematician. Usually talk about a normal curve or a bell-shaped curve that has that nice curvy bell shape. Is a bell-shaped curve with the total area under the curve is 1. The curve is symmetric about the mean. So notice in the middle, I went ahead and put like this line down the middle. So in the middle is our mean. Remember, our mean is our mu value, and it's always in the middle. So notice it has 2 tails. So these 2 tails of the curve extend indefinitely, and the areas are so close to 0. So notice on the left-hand side, it's going to go on forever to the left, all the way towards negative infinity. On forever to the right, all the way towards positive infinity. If we're talking about the area under the curve, if these are going all the way out, it's kind of like an asymptote. Though you took college algebra, we talked about asymptotes or pre-calculus, where it gets super, super close to this x-axis, but it doesn't touch it. So it gets so close that there's essentially, like when we round it, there's no area. We just consider that area 0. So it's so, so, so small. And the probability that a continuous random variable assumes a single value is always 0. They have to be intervals, which kind of makes sense because think about it. If you have a single value, let's say like something right here, and this is going to be x, right? We're talking about the area. Well, if we just have one single point, there's not an area. It's not from this point to this point. There's no area there. It's just one single line. So if there's one single line, that means there's no area. So no area means that it's always 0. So single value is always 0 because there's no area to look for. So I do want to draw a little picture because notice that there's a horizontal asymptote here. It's going to get super, super close to this bottom, but it's not going to touch. Horizontal asymptote means it gets super close. But does not touch. Gets super close but doesn't touch. One more thing I want to mention is we said if the total area under the curve is 1, the whole thing is 1, and we know that in the middle is our mean. So it means it's the same thing on the left side of the mean, same thing on the right side of the mean. So if the whole thing's 1, that means this is 0.5, and this is 0.5. So both halves together would give us 1. So the graph of any normal distribution is symmetric about its mean. Then the area under the curve, we just talked about this, under the curve to the left of mu is going to be half, so 0.5. And the area under the curve to the right of our mean is also going to be 0.5. So with any continuous distribution, probability is determined by calculating the area under the curve. So notice I bolded it, but this is something that I might even highlight too because it's so important. Probability is always the area under the curve. Probability is always the area under the curve. So for instance, if we calculate the probability that A is less than X is less than B, so the probability that X is between A and B, we needed to determine the area under the curve between A and B. Let's visualize it. Let's draw this on this picture to help us. So in the middle, if we have our mean, because we always have our mean in the middle, and let's say that our A value is over here and our B values over here. A and B are just numbers in general. So to find the probability that X lies between A and B means that we are going to find the area between A and B. Area between A and B. So notice it's the shaded area. That's what this chapter is all about. So in any normal distribution, so normal distribution has this nice bell-shaped curve. The probability of X assuming a single value, which we talked about up here, if it's a single value, just A, that means there's no shaded area. So if there's no shaded area, it's going to be 0. So the probability of X assuming a single value is always equal to 0. That means the probability of X equaling A is going to be 0 for any value of A. So if it's just 1 point, that means that the probability that A is less than or equal to X and less than or equal to B, that X is between A and B, including A and B, those endpoints, the A and the B, it doesn't matter if it's included or not, because if A is equal to or B is equal to, or if it's not equal to, that area is going to be 0. So we're not adding anything to it. Moral of the story, the probability of A is less than X is less than B is the same thing as the probability of A is less than or equal to X, less than or equal to B. It doesn't matter about that equal sign. It doesn't matter about those endpoints because those are just single values. Those are single points. And we know that that area is 0. So we're not adding on anything to it. Same thing. For the probability that X is greater than or equal to B is the same thing as just saying the probability of X is greater than B. Moral of the story. The endpoints are single values. So the area equals 0. So it doesn't matter if we're equal to or not. So all symbols are the same. Clean up. So if it's less than or equal to, will be the same as just less than. Greater than or equal to will be the same as greater than. That or equals to doesn't matter. It's a single value. At a single value, our area is 0, so it doesn't change our answer. It doesn't change that shaded area. So let's start trying to find some of these probabilities. It says determine the following probability. What's the probability that our Z value equals negative 1.92? So I have a single value. What's the probability of a single value? 0. So done. Probability that Z is 5.69? 0. These are single values. So the area is, so area equals 0. If the whole test was like that, we would be good. I know, that's only page 1. Questions, comments, concerns so far? All right, page 2. All right, still talking about our normal distribution, our normal curve. The shape of a normal curve is determined by the standard deviation. Remember, standard deviation is our sigma. So standard deviation is talking about how spread out the graph is. That's our spread. The standard deviation is our spread, where the position of the normal curve is determined by its mean. Remember, our mean is our mu value. It's centered about the mean. So here's some examples to show you. We have our normal curve, and then notice it's two values. So for this, it's going to be our normal curve, then our mu value, our mean, then our standard deviation. N is for normal, then it gives us our mean, then our standard deviation. So notice for this first example, so our solid line has a mean of 0 and a standard deviation of 1. The dashed line over here to the left has a mean of -2 and a standard deviation of 1. And the dotted normal curve over here has a mean of 1 and a standard deviation of 1. So notice for all of them, they have the same standard deviation. So they have the same shape. It's the same exact width. It's the same spread. Same standard deviation. So same shape. Just notice that they are shifted left and right. Their position is different because our mean is different. Remember, it's centered around our mean. So our solid line is centered around 0. Our dashed line is centered around -2. And our dotted line is centered, or dotted curve, I should say, is centered around 1. So that just shifts it left and right. It changes our position. So we have different means. So we have different positions. Different positions just means it's shifted left and right. All right, so taking the same concept and looking at the next group of examples. Looking at the next curves. Thank you so much for coming. See you tomorrow. So for these, remember that it's our N is our normal curve, then it's our mean, and then it's our standard deviation. So notice for all of them, our mean is the same. Our mean is 0. So they are all centered at 0. Same mean. So same position, which is centered at 0. And then for our standard deviation, for our first solid line, it says our mean is 0 and our standard deviation is 1. For our dashed line down here, it says our mean is 0 and our standard deviation is 1.5. So think about it. We stretched it out. Remember we talked about a lot of you had college algebra with me. We talked about stretching and shrinking. That's what it is. We're stretching it horizontally. So if we take it and we stretch it horizontally, that's what makes it look wider. And then our dotted line, which is this tall one, our dotted curve, has a mean of 0 and a standard deviation of 0.5. So that means we took it and we had a smaller spread. So we took it and we shrunk it. Whenever you take it and you shrink it, it's got to go somewhere. So that's why it looks taller. Think about like a rubber band. Whoa. if you take this regular circle, like here's our normal circle, right? And then if you stretch it out, notice it gets, as you stretch it, it's gonna get shorter and shorter and shorter. And then if you take our regular normal, and if you compress it together and shrink it, it's gonna get taller and taller and taller. So that's why this one looks taller. So let me write that as a little note. We have different means, I'm sorry, different standard deviations. So different spreads. There's going to be a stretch or a shrink. A stretch or a shrink. I know it kind of sounds stupid, but this is what helps me, so maybe it might help you. I think of shape and then standard deviation both start with S, where position and mean, like this is the other one. But shape and standard deviation both start with S. That's how I remember which one's which. All right, so we talked about normal distributions. We have this bell-shaped curve. But we also have is kind of like our parent function, going back again to college algebra, kind of like our parent function. If you have a standard normal distribution, a special case of this, a standard normal distribution is a special case of normal distributions. It's just kind of like a specific type of normal distributions. So for standard normal distributions, our mean is always 0. And our standard deviation is always 1. So that's what gives us this solid shape, solid line. Whenever it's standard, we show that it's standard by using the variable z. So instead of x, we use z to show that it's standard. Values that are negative are to the left of the mean because the mean is 0, so to the left of 0 or negatives. But under the area under the curve is always, area is always positive, no matter what. Our area is always positive. So let me just write that down. So remember, our mean is 0, and the area under the curve is always positive. Area in general is always positive. We talked about using the letter z. So we have our z-scores. A z-score is our standardized value because z means that it's under our standard normal distribution. It's measured in units of standard deviation. So if z is 1, that means 1 standard deviation. If z is 2, that means 2 standard deviations. And it indicates how many standard deviations above the mean, if it's positive, and then the mean if it's negative. So how far above or below an observation is. So we have 3 basic probability scenarios. The first one is our probability that z is less than a. Probability that z is less than a. The next one is the probability that z is greater than a. And last but not least, the probability that z is between a and b. The probability that z is between a and b. Where a and b are just numbers. And z is our arbitrary, so in general, g score. In general, z score. So this is just kind of like the definition-y type stuff. So to solve, we need to find the area under the curve. We have 2 options to do that. We can either use the table, which is this last thing on our notes packet. Here's our table. Just like we talked about on last test, you can either use a table, which gives us the area under the curve to the left of z. Make sure that you realize it's always to the left. We'll talk about that in a second. Or you can use your calculator, whatever preference that you like, totally up to you. But you have 2 options, either the table, which you will have on the test, or a calculator, which you're also able to have on the test. So for our calculator, just because I'm here, let's just write it. In order to get to our calculator, we're going to hit our second button, and then our vars button. Notice second vars tells us our distribution, so that's how I know. Above vars says distributions, so second vars. We're talking about normal curves here, and we're talking about normal continuous curves. So normal continuous, we're going to go down to number 2, which is normal CDF. And then whenever you press that, if you have a newer calculator like mine, it will like write out, it'll ask you what it wants. If you have an older calculator, it's still going to do the same thing. You just have to program it. It doesn't like label it for you. You just have to know what order is which. So it's going to tell us our lower, which is our lower boundary, our upper, which is our upper boundary, our mean, and our standard deviation. Our mean and our standard deviation. All right, let's actually do an example. So the first example, straight from the homework, says that find the area under the standard normal curve. By the way, whenever it says standard, I know I'm going to use Z. To the left of Z, which is negative 1.02, round our answer to 4 decimal places. All right, whenever we use Z, we know it's standard, and the problem told us. So that tells us automatically that our mean is going to be 0 and our standard deviation is going to be 1. So it kind of tells us that without actually writing it out. Notice it's really important. It's super, super helpful to draw our graphs. So I put a graph on every single example. And I had someone ask me like, oh, it's really helpful like for the picture to be there, but I'm not good at drawing the picture. And I'm like, I'm not either. It doesn't matter how you draw it. But I put a printout of like a bunch of these images on one sheet. So that way, if you're working on your homework and you want to print out a couple of those pages, then you can just work on every problem a different image on Blackboard. So it's on Blackboard if you want it. Some people are like, I don't care what it looks like. I just want to get it done. That's fine too. But if you want a bunch of these printed out, and it's on Word, so you can like edit it and do whatever you want. But I thought that might be helpful. So under test 3 in Blackboard, you'll see normal distribution, bell-shaped curve, handout or something I put on there. And there's just a bunch of these pictures on one page. All right, so in the middle we know is our mean, which we know is 0. Our Z value is negative 1.02. So because it's negative, I know it's to the left of 0. So somewhere over here, I don't really care where it's at as long as it's to the left of 0. So here's our Z, which is negative 1.02. And the problem says, find the area under the curve to the left. So our shaded area is going to be to the left. It tells us to shade to the left. Remember that our graph goes on forever to the left, all the way towards negative infinity. So that's our picture. We have 2 options to find the area. We can either use our Z table or our calculator, whichever one you like better. I'm going to show you both. So on our table, let's start there. On our table, it tells us it's a Z table, and we know that our Z value is negative 1.02. Our Z value is negative 1.02. All right, so going to our Z table. So notice on the front side is our negatives. So there's negatives on one side and positives on the other. So go to the negative side. Notice up here it shows you a picture. This picture is really helpful. It says the entries in this table on this page give the cumulative area under the standard normal curve to the left. So it only gives us the areas to the left, which this problem was the area to the left. So it gives us our answer. So let's find when Z is negative 1.02. So notice this Z column right here will give us our ones and our tens place, and then this will give us our thousands place. So go down to negative 1.0. and then we're going to go over to 2. So that will give us negative 1.02. So boom, there's our answer, 0.1539. Thanks, Lonzo. I'll see you tomorrow. Oh, thanks. So this answer tells us the area to the left of that z-value, and that's what we're looking for, so that's our answer, done. Again, one more time, it's negative 1.0, and then we're looking at our thousandths place here, which gave us the 2, and that's our answer, 0.1539. Questions about the table? It's kind of straightforward for this problem.
We can't use it though, it's to the right, right?
Yes, you can use it. We're going to do it next. It's just a little bit more work. But you can also use your calculator.
I know you said the steps, but
Yeah, we're going to do that one right now.
and then also put in the other spot.
Yeah, I'll show you. All right, so here, this gave us our answer, which is 0.1539. Sorry, I think that's you. I know, the calculator sometimes is easy because it's a little bit more straightforward. So let's do it on the calculator as well. So on the calculator, oh, hey, Jackie. All right, so we talked about it up here. We went second vars down to normal CDF. I'm just gonna go ahead and write down what we're gonna put in our calculator. I guess I'll go here. So just to reiterate, I want my distribution. So distributions is right here above vars. So second vars, and then go down to number 2, which is normal CDF. We're talking about a normal continuous curve. So that's why it's normal CDF. Press enter. So again, if you have a newer calculator like mine, it'll ask you, which this is why it's more money, because it makes it worth money. It asks you lower, upper, mean, and our standard deviation. So lower means our lower boundary. So notice in my calculators, -1 e to the 99th. That means -1 times 10 to the 99th power, which is essentially negative infinity. But a lot of times it's like too much work to put that in. So a lot of times whatever I use for negative infinity is -99999. I just put a bunch of 9s just because it's easier than typing in the E. If you want to do the E, you're more than welcome to. It's right here above the comma. And E is like our scientific notation. But do you need it? No, because it's like a lot of extra points. Just plug in -99999. It doesn't matter how many 9s, just put a bunch of them to stand for negative infinity. Yes, sir. Yeah, sure, you can. But remember, once it gets so big, you're going to round it. So it doesn't really matter. As long as you put like a handful of 9s, you're good. It'll give you the same answer. But yeah, you're more than welcome to use the caret symbol. That's a great way to make it even larger if you want to. Yeah, you can leave it. But every time you change it, it's going to like go back to what you previously put. Like, so like if I do this problem again next, it'll come back to like this answer. I'll show you. Okay. But yeah, if it's already there for you, just leave it. So this is our lower boundary. The reason why it's our lower boundary, we're talking about this area. So the area to the left, this is going from left to right, our smallest to our largest, just like an interval notation. And I'm like referencing a lot of algebra today. But it's going down to negative infinity. We can't put negative infinity. We can't put negative infinity into our calculator, so we put -99999. Our upper boundary is this -1.02. Our upper boundary is -1.02 because we're saying that it's in between those two values. We said that it's normal, so our mean is 0 and our standard deviation is 1. So -1.02 for our upper Mean is 0, standard deviation is 1. Notice whenever I go down to paste and press enter, it gives it to me exactly like I have it written, and that's exactly like how it would be if you have an older calculator. And then press enter. Boom, there's our answer. 0.15386, which rounds to 0.1539. So either way, you get 0.1539. Either way. So that was area to the left. Questions on area to the left. We're going to do our other two scenarios. Right and then the middle. The next one is find the area under the standard normal curve. Again, it says standard. So again, we're going to use z values. To the right, so this time we're going to look to the right, of z equals 1.39. Round our answer to 4 decimal places as needed. So in the middle, we know is our mean, which is 0. Our z value is positive 1.39. So our z value is somewhere over here, positive 1.39. And we're looking at the area to the right. So I'm going to shade in the area to the right. Notice this graph goes on forever, and we're going on forever to the right. So we're going on forever towards positive infinity. Towards positive infinity. So remember when we're having z, that's telling us it's standard. So it's telling us that our mean is 0 and our standard deviation is 1. So I'm going to show you both ways. On the table, we're going to look for when z is positive 1.39. But remember, that's going to give us the area to the left. So let's see what it gives us, and then we'll talk about the area to the right. So on the table, we're going to look for when z is 1.39, and that'll tell us the area to the left. So positive, when z is positive, we're going to go down to 1.3, and we're going to go over to 0.9. So down to 1.3, over to 0.9, and that will give us 0.9177. So 1.39, 0.9177. But remember, that's area to the left. 0.9177. We need to find, so that's all of this. We need to find whatever is left over. So I know the whole thing's 1. So if the whole thing's 1 and we're trying to see whatever is left over, in order to find the area to the right, we're going to do 1 minus. So 1 minus 0.9177. Again, the whole thing's 1. We know that this area on the left-hand side is 0.9177. So that means this area that's left over has to be whatever's left over to make 1. So that's why we did 1 minus. So in our calculator, 1 minus 0.9177 will give us our answer of 0.0823. So that's how we do right on our table. So on our calculator, nothing's changed on our calculator because we're going to tell it left and right what our boundaries are. We're still going to go to normal CDF. Remember, normal CDF is second vars going down to normal CDF. So now our lower boundary, going from left to right, the graph starts on the left-hand side at 1.39. Our upper boundary is going to go on forever towards positive infinity. So now positive infinity we can show in our calculator as 99999 positive. to show our positive, really big number, positive infinity, which is our upper boundary. Our mean is still 0, and our standard deviation is still 1 because it is normal. So going down to paste, no matter if you have an older calculator or a newer calculator, it should all look like this. Pressing enter, we get 0.08226, which would round to 0.0823. So same answer, either way, whatever floats your boat. So we talked about area to the left, we talked about area to the right. On the next page, we're going to do our third scenario, which was the area between the two. The area between two values. Going up here, remember we said we had 3. We talked about area that's less than, that's area to the left. Area that's greater than, it's area to the right. Now we're talking about area that's between the two. Questions on this page before I go to the next page? All right, let's just knock out this last page and then we'll take a quick break, come back and finish. So the area under the standard normal curve. So again, we're talking about standard. So we have our z values. Z we know tells us that our mean is 0 and our standard deviation is 1. So find the area under the standard normal curve between z equals negative 1.93 and z equals positive 2.4. Round the solution to 4 decimal places as needed. So in the middle, we have our mean, which is 0. Our first z value is negative 1.93. It's negative, so it's on the left-hand side of 0. So somewhere over there is fine. Doesn't really matter where. We're just using it to see our lower and our upper boundaries. Our other z value is positive 2.4. So somewhere over here on the right-hand side of our 0. And we're trying to find the area between the two. The area between the two. In my opinion, this is where our calculator really comes in handy. But I'll show you how to do it on the table. All right, so let's look on the table when z equals negative 1.93. What's our answer? And when z is positive 2.4, what's our answer? Remember, this answer is going to tell us their area to the left. The table is going to tell us our area to the left. So I'll give you a minute, and then I'll go to the table. All right, so on the table, I have negative 1.93. So looking at my negative side, we're going to go down to 1.9, and we're going to go over to 3. So down to 1.9, over to 3. Boom, there is our value, 0.0268. 0.0268. So same thing for now, positive 2.4. So it's the same thing, by the way, as positive 2.40. So we're going to go to our table. On the positive side, we're going to go down to 2.4, and we're going to go over 0, so 2.40. So that'll be this first one, 0.9918. So 2.40 would give us 0.9918. So 0.9918. All right, so let me kind of show you on the picture on the graph what it would look like. So area to the left of 2.4. So from here all the way over would give us 0.9918. That's area to the left. So to the whole left of 2.4, going on forever. And then to the left of negative 1.93, so from here to the left, would give us an area of 0.0268. But remember, we're trying to find the area between the two. We're trying to find the area between the two. So to find the area between, we're going to subtract. So our area between, we're going to subtract. So 0.9918. So it's all of this, but it wants it to take out this piece that's not shaded. So take out 0.0268. So subtracting those two, 0.9918 minus 0.0268, and that will give us our answer of 0.965. 0.965. So that's using our table. Using our calculator, nothing's new. We still have our normal CDF. Normal CDF. So second bars going down to normal CDF. Remember again, it's second bars to give us our distributions, going down to number 2, which is normal CDF. Our lower limit, so looking at it from left to right, our lower side of our shaded area is negative 1.93. Our upper limit, it's stopping at positive 2.4. Our mean is still 0, and our standard deviation is still 1. So going down to paste, that's how it's going to look for everyone, no matter what calculator you have. Boom, there's your answer, 0.96499, which is going to round up to 50. So our answer either way is 0.9650. Because I put the 0 because it says round to 4 decimal places, so 4 numbers after the decimal. So that's all of our options. We did to the area to the left, we did area to the right, and we did the area between. That's pretty much chapter 6. So our last 3 examples are talking about the empirical rule that we talked about in test 1, I think. 1. All right, so it's just showing you where it comes from. So find the area under the standard normal curve within 1 standard deviation of the mean. Round the solution to 4 decimal places as needed. This is where the values for the empirical rule originated. So by the way, this word within means above and below. Means above and below. So 1 standard deviation, remember standard deviation is our z values. So 1 above would be positive 1, and 1 below would be negative 1. So it's telling us in that sentence that z is positive 1 and negative 1. It's also telling us that it's standard. So standard means that our mean is 0 and our standard deviation is 1. So we're going to do this exactly like we did the other ones. So in the middle is our mean, which is 0. If our z value is negative 1, that's going to be to the left-hand side. And z value of positive 1 is to the right-hand side. It says within, so that means between these 2 values. Now, for time's sake, a lot of you said that you like the calculator, so are we good to just go with the calculator? If you want to do the table, that's fine too. You would just find the area and then subtract the 2. I feel like it's kind of dumb because if you use a table, you still have to use your calculator, right? I mean, I don't know, maybe I'm bias,
And
but
what if you type it in wrong? There's a lot more mistakes.
yeah. So on our calculator, I'm going to show you, by the way, just because I know it's coming up. So remember, P is our probability. Probability is our shaded area. That are Z values within. So one below, one above. So -1 is less than Z is less than 1. So same thing on our calculator. We're still going to do normal CDF. Our lower limit's -1. Our upper limit's +1. Our mean is 0. And our standard deviation is 1. So in our calculator, second vars go down to normal CDF. Our lower limit means the lowest boundary, like where it starts off on the left-hand side, which is -1. Our upper boundary is +1. Our mean is still 0, and our standard deviation is still 1. Pressing paste, pressing enter, there's our answer. So our area is 0.68268. So that 6 is going to round up to 7. So 0.6827. You're like, what? I don't remember that being empirical rule. Remember, empirical rule means within one standard deviation was 68%. So turning this into a percent, moving our decimal 2 places to the left, this is what gave us that 68% for our empirical rule. So same thing for the next one, but instead of within one standard deviation, now we're looking within 2 standard deviations. So find the area under the standard normal curve within 2 standard deviations of the mean, round to 4 decimal places as needed, and this is where we get our next empirical rule from. So within 2 means that our Z value is going to be +2 and -2. It also tells us, because it's Z, that our mean is going to be 0 and our standard deviation is 1. So in the middle is our mean, which is 0. We're looking at Z is -2 on the left-hand side because it's negative, and Z is +2 on the right-hand side because it's positive. Our pictures aren't as important on this one because it's between the 2, but we're still, for consistency's sake, going to do it. So on our calculator, again, we're looking for the probability that Z is between -2 and +2. Remember, our probability is our shaded area. I don't like how I do 2 different 2's. We're still going to do normal CDF. Normal CDF is second vars, going down to normal CDF. Our lower limit, our shaded area starting on the left-hand side at -2. Our upper limit starting ending on the right-hand side at +2. Our mean is 0 and our standard deviation is 1. So if you have an older calculator or a newer calculator, this is what it should look like. Normal CDF, -2, +2, 0, 1. Pressing enter. There's our answer. Area 0.95449. So that second 4 is going to round up to 5. And then remember, empirical rule told us in percentage form. So that would give us that 95%. That 95%. Last one. So find the area under the standard normal curve within 3 standard deviations of the mean around our solution to 4 decimal places. And again, this is where our last empirical rule came from. So within 3 means that our Z value is going to be +3 and -3. Because we're talking about Z's, that means our mean is going to be 0 and our standard deviation is going to be 1. So on our calculator, before I go to a calculator, let's show a quick picture. Our mean is 0. Our z could be -3, and z is +3. So on the left and right hand side of our middle mean, we're trying to find our probability. Probability is the shaded area between the two. So that means our probability, which is our shaded area, of z is going to be between -3 and +3. So probability that -3 is less than z is less than 3. Remember, if we said less than or equals 2, it doesn't matter. It still would give us the same answer. We're still going to do normal CDF. Our lower limit's -3, our upper limit's +3, our mean is 0, and our standard deviation is 1. So in our calculator, second bars, going down to normal CDF, our lower limit is -3, our upper limit is +3, our mean is 0, and our standard deviation is 1. Pressing paste, pressing enter, we should all come to the same answer of 0.9973. And turning this back to the empirical rule, turning it into a percentage, we said for within 3 decimal places, it would give us 99.7%. 99.7%. Questions, comments, concerns for me so far? If not, let's pause right there. Let's take a quick, because we got more to do, quick 5-minute break, and then I'll come back and we will start off with page 4. All right, so picking up where we left off on page 4. So given a standard normal distribution, determine the following probability, round to 4 decimal places if needed. It's the same concept, they just kind of like worded different. We know it says probability that z is less than or equal to negative 1.1. So we know that probability, red pencil. Probability is our shaded area. Probability is our shaded area. It tells us that it's z. Z is telling us that our mean is 0 and our standard deviation is 1. And I also want to make the note, remember we said that z being less than or equal to negative 1, it doesn't matter equal to negative 1.1 because it's going to be the same thing as just less than. So it's going to be the same as the probability of z being less than negative 1.1. So either way, it's going to give us the same answer. Thank you. So again, the following probability means shaded area. So in the middle is our mean, which is 0. Then we have a z value of being negative 1.1. So negative, so it's on the left-hand side. Here's our z, negative 1.1. And we're saying that it's less than. So less than means everything to the left. It's going to go on forever towards negative infinity. So that'll be our lower boundary. And again, for time's sake, I'm just going to use our calculator. The other reason why I like the calculator better is because our calculator will work every single time, no matter what. Our table's only so big and so small, so there's only so many z values. So we'll see in a minute where our z value might not be on our table, so we have to use our calculator. So that's kind of like the reason why I kind of default always back to my calculator, because that will work every single time, no matter what. So, but if you want to do your z table on this one, you do you. So on our calculator, we're going to do normal CDF. Normal CDF. Our lower limit's negative infinity. I can't plug negative infinity into my calculator, so I'm just going to do a super, super small number, so negative 99999 to account for negative infinity. Remember, this is our lower boundary. Second bars, normal CDF. Negative 99999, doesn't matter, just put a handful of nines. You're going to round it anyways. Our upper limit, so it's stopping on the right-hand side at negative 1.1, which is our upper limit. We're talking about z, so our mean is 0 and our standard deviation is still 1. We'll see later what happens when our mean is not 0 and our standard deviation is not 1, but for now, that's what it is. So if you have an older calculator or newer calculator, it should all look the same. Boom, there's our answer, 0.13566, which will round up to 0.1357. Same thing for the next one. So I'll give you a question, but it kind of gets boring.
So we don't have to do the empirical level, not the method.
Yeah, we don't have to do all that stuff. It's just, those were like specific examples. This is just in general. So thank you for asking. So given a standard normal distribution, determine the following probability, round to 4 decimal places as needed. The probability that z is greater than negative 2.34. So in the middle is our mean, which is 0. Our z value is positive, so on the right-hand side, z value is positive 2.34. And we're saying that z is greater than. So greater than means everything on the right-hand side going on forever towards positive infinity. So again, on our calculator, we have our normal CDF. So second VARs, going down to normal CDF. Our lower limit, looking at the left-hand side, our graph starts at positive 2.34. Our upper limit's going on forever towards positive infinity. I can't plug positive infinity into my calculator, so I'm going to plug in a really, really big number. So 99999, just a handful of nines, to represent positive infinity. Our mean is 0, and our standard deviation is still 1. So once I go down to paste, all of our calculators should look exactly the same. Pressing enter, boom, there's our answer, 0.00964, which would round to 0.0096. Same thing for the next one. Given, so we did left bound, we did right bound. Now we're going to do center again in between. So given the standard normal distribution, determine the following probability, round to 4 decimal places as needed. Find the probability that 0.089 is less than or equal to z, is less than or less than 0.97. So z is going to be between those two values. So in the middle is our mean, which is 0. Our first z value is positive 0.89. So somewhere over here on the right-hand side of our mean. Our second z value is 0.97. So on the right-hand side of the other z value. So our mean is going to be between the two, which is fine. It's okay. They're both on the same side. It just means that that is going to be something that's less than half, less than 0.5. So on our calculator, we have normal CDF. Our lower boundary on the left-hand side is 0.89. Our upper boundary on the right-hand side is 0.97. Our mean is 0, and our standard deviation is 1. So on our calculator, second VARs, normal CDF, lower 0.89, upper 0.97, mean is 0, standard deviation is 1. Boom, there's our 0.02070, which would round to 0.0207. So remember I said on these three, our z values were decent enough that we could use our table if you wanted to, or the calculator, your choice. But let's look at the next one. It says, given the standard normal distribution, determine the following probability, round to 4 decimal places if needed. Our probability that z is less than negative 0.852. On our table, negative 8 isn't on our table. The smallest thing is negative 3.4. So you don't have the option. You have to use our calculator. That's too small for our table, which is the same thing we've been doing. Nothing changes. So that's kind of nice. That's kind of why I like using the calculator. So on our calculator, let's draw our picture. And the middle is our mean, which is 0. Negative 8.52 is somewhere really small. So somewhere over here on the right-hand side, that z value is negative 8.52. We're saying that z is less than, so everything to the left-hand side, going on forever towards negative infinity, going on forever in the negative direction. So on our calculator, we're still going to do normal CDF. So second VARs, normal CDF. Our lower limit, looking at our graph on the left-hand side, it's going to go on forever towards negative infinity. So negative 99999, a handful of nines to represent negative infinity. Our upper limit, our shaded area stopping at negative 8.52. So our upper limit's negative 8.52. Our mean is still 0, and our standard deviation is still 1, because we're talking about z. Pressing paste, all of our calculators should look exactly the same, which is what we have written. Pressing enter, we have 0. So this just means that our area is so small that it pretty much is 0, rounds it to 0. Our calculator only has so much room, so instead of saying 0.000, it just rounds it. So I also want to put a note here that our z value is too small for the table. But you can't always assume that, okay, it's not on the table, so the answer is 0 is the problem. But yeah, because it's so small, that's why we don't bother putting it on the table. The z value is too small for the table, so we're going to use our calculator. Okay, that's a too small example. Next, we're going to see a too big example. So before we go there, questions on this page? Yes, ma'am. The second one?
How it was on the right, on the previous question.
Uh-huh.
When we did it with the table and we said when it's on the right, we did 1 minus 7
Right. Because we didn't use the table here, we only used our calculator. So
if we had used the table.
Yep, if you use a table, you would find out what's the z when z is 2.34. So positive 2.3 and then over to 4. And then there's your answer, so 0.9904. Because it's area to the right, we would have to do 1 minus 0.9904. And that's what would give us that same answer. But instead of having to worry about when do I do 1 minus and when do I not do 1 minus, our calculator does that for us. So we don't have to worry about 1 minus when you do our calculator. That's what the lower boundary and the upper boundary are for. But as you can see, if you use your table, you still get the same answer. Thank you for asking. Just like this one, you would subtract the two areas. But again, our calculator, we don't have to worry about that because our calculator does that math for us. Ryan. What do you mean, like if we have more than one table?
Like you said that is 0 because it is so small.
Right.
For our calculator.
Right.
So,
because z is negative 8.52. You're saying like what value should that be that it's going to be too small? Yeah. Okay, so our table only goes to negative 3.49. So anything less than negative 3.49. Likewise, our table on the big side only goes to positive 3.49. So anything bigger than 3.49, we'd have to use our calculator, which is the next example. So great question. Anything else? So great segue, thank you. Into the next problem. I'll pay you later. So given a standard normal distribution, determine the following probability, round to 4 decimal places as needed. We have the probability that our z value is less than or equal to 9.18. So 9.18, like we just talked about, is too big for our table. So because we can't use our table, we have to use our calculator. The good thing is we've been using our calculator anyways, so nothing changes. So in the middle is our mean, which is 0. Our z value is 9.18, which is too big, so it's really big. So somewhere like way over here on the right-hand side is going to be our z value, which is 9.18. And we're saying that z is less than or equal to. So less than or equal to means that we're going to shade the left-hand side. So if you notice, I'm shading most of my graph. And it goes on forever towards negative infinity. So on our calculator, Again, we have our normal CDF. We have normal CDF. So normal CDF. Our lower boundary, it's going on forever to the left, so negative infinity. So we're going to put negative infinity as negative 99999 into our calculator. Our upper limit is positive 9.18. And our mean is 0 and our standard deviation is 1 because it told us Z. Pressing paste, all of ours should look the same. Pressing enter, boom, our area is 1, which makes sense because it's most of our graph. So if it's most of our graph, we know all of our graph is 1. So whenever we round it, that's why we get to 1. One more time, I'm going to put on here, it's going to be too big. Our Z value. I'm trying to word it the same that I did on the previous page. Our Z value is too big for the table. Our table only goes up to 3.49. So you're going to use your calculator. All right, last call for questions before we take this and add on one more thing to it. This next thing that we add on to it is really, really, really going to be helpful for our calculator. So really the table, I mean, if you really want to use a table, go for it, but your calculator is going to save you a whole lot of time. All right, so everything we talked about so far is Z values. Z values means that it's standard. Standard means that our mean is 0 and our standard deviation is 1. But what if we don't have a Z value? If we don't have a mean of 0, what if we don't have a standard deviation of 1? So that means we have to standardize it. So standardizing a normal distribution converts a regular distribution to a standard normal, which makes our calculations a lot easier. So in general, we usually use X. So it's changing that X value to a Z value. So we know for Z values, our mean is 0 and our standard deviation is 1. For X values, our means could be anything and our standard deviations could be anything. So to do this, we have our formula, and this formula was on our formula sheet. Z equals X minus our mean all over our standard deviation. That's on our formula sheet. Note the formula converts an X value, which could be measured in anything, dollars, pounds, whatever the context of the problem is, where Z values are our standard deviations, and for our standard deviations, our mean is 0 and our standard deviation is 1. So here's the good thing. This is why these calculators are so expensive, but they're worth every single penny, because our calculators could do that for us. They change X to Z behind the scenes, but our table doesn't. Our table only uses Z values. So let's do an example and then I'll talk more about it. So it says, assume that X is a normally distributed continuous variable with a mean of 86 and a standard deviation of 11. Notice it's just normal, it's not standard. So determine the following probability, round to 4 decimal places as needed. So it says the probability that X is less than or equal to 72. So notice this next line, I copied it straight from the homework, says what's the probability that Z is less than or equal to blank? So it's asking us to convert this X value of 72 to a Z value, which is fine. We can just plug it into that calculator. So to convert X to Z, I'm going to plug it into this formula right here. So we know that Z equals our X minus our mean all over our standard deviation. So X, they told us, was 72, minus our mean, they told us, was 86. All over our standard deviation, they told us, was 11. Whenever you put it into your calculator, make sure that it's a fraction. So put the top in parentheses. So 72 minus 86 in parentheses, divided by 11. And that will give us negative 1.2727. So what's the probability that z is less than or equal to negative 1.2727? Now it's in a z value. So now our mean is 0 and our standard deviation is 1. We standardized it, so we made our mean 0, we made our standard deviation of 1 by turning it from x's to z's, and now it's exactly like the previous problems we've been doing. So in the middle is our mean, which is 0. Remember, we're talking about probability. Our probability is our shaded area. Our z value is negative, so on the left-hand side, negative 1.2727. And we're saying that z is less than or equal to, so everything to the left. Going on forever towards negative infinity. So exactly like the previous problems, there's that one extra step. So on our calculator, we have our normal CDF, which we get to by doing second button and then the bars button. Going down to normal CDF. Our lower limit, looking at the left-hand side of our shaded area, is negative infinity. So we're going to plug that into our calculator by negative 9.99999, handful of nines. And it stops at our upper boundary of negative 1.2727. Our mean is 0 and our standard deviation is 1 because we standardized it. So because it's now z. So negative 99999, negative 1.2727 is our upper. Our mean is 0 and our standard deviation is 1. So exactly like our previous problems that we did, boom, there is our answer, 0.10156, which will round up to 0.1016. So because we found a z value, you could plug this into the table and you can use a table as well. But notice the next one, it doesn't ask us for that step. It doesn't make us turn it into a z value. It just says, what's the probability that z is greater than or equal to 1959? And it doesn't ask us for this step to convert it to z. So forget the table, because that'll be one less step. We can plug all of that into our calculator. Let me show you. So assume that x is a normally distributed continuous variable with a mean of 1850 and a standard deviation of 110. Determine the following probability, round to 4 decimal places as needed. So again, if we didn't have our calculators back in the day, we'd have to convert it to z, then look at our table, and then go 1 minus, because it's looking at the right-hand side. But now our calculator will do all of that for us in one shot. Let me show you. So because we're looking at x, it tells us in the problem our mean's not 0 anymore. Our mean is 1850. So in the middle is our mean, which is 1850. And our standard deviation is 110. So in the middle is our mean, which is 1850. Right. So like this one asked us, like this was like part A, and this was part B. Like this asked us to convert it to z. This one doesn't ask us to convert it to z, so we don't have to. And like this is exactly how it'll look like on the homework, except I put in the picture of the curve. So yeah, because this one didn't ask us for our z value, we don't have to convert to z. You write that as a note. This problem did not ask us to convert x to z, so we can skip that step. And plug it all into our calculator. And that's why this calculator is mandatory for this class. You don't have to buy a textbook, but you have to buy the calculator because it does the problem for us. So it's worth every single penny. All right, so our X value is 1959. 1959 is greater than 1850. So our X value is going to be on the right-hand side of our mean. So somewhere over here, X value is 1959. And we're saying that X is greater than or equal to. So greater than or equal to means everything on the right-hand side going on forever towards positive infinity. And even though we're not using Z, we're going to plug it into our calculator exactly the same. Nothing changes, which is nice that we're doing the same thing every single time. So on our calculator, we have our normal CDF. So still second bars going down to normal CDF. Our lower limit, looking at the left-hand side, is 1959. So still the same. Our lower boundary. Our upper boundary is infinity. So I'm going to plug in infinity into my calculator as 99999 to represent infinity for our upper boundary. Oops. 1959 is our lower. 99999 is our upper. Our mean, though, this time, our mean's not 0 and 1 because we don't have Z values, we have X's. Our mean is 1850. And our standard deviation is 110. So, but our calculator has this formula plugged in. So behind the scenes, it's going to convert X to Z, do all this hard stuff for us. Boom, there's our answer. So we don't have to do any extra steps. It will do it for us. So 0.16086, which will round up to 0.1609. Love it. Let's do another one. We have one more that's straightforward, and then the rest of them are the same exact concept, but they're just not as straightforward. Before I go to the next page, questions on this one? Kind of wrote that so you can see it if you need to. All right, so on the next page, it says that assume X is a normally distributed continuous variable with a mean of 99 and a standard deviation of 9. Determine the following probability, round to 4 decimal places as needed. All right, so because it's X, we know that our mean, which they give us, is 99, not 0, and our standard deviation, which they give us, is 9. So in the middle is our mean, which is 99. X is in between 76 and 97. We're trying to find the probability that X is between 76 and 97. So 76 is so somewhere over here. 97 is also smaller, so still on the left-hand side of our mean. And we're trying to find the area between the two. So on our calculator, we have our normal CDF. Second bars, normal CDF. Our lower limit, looking at the left-hand side of our shaded area, would be 76. Our upper limit, looking at the right-hand side of our shaded area, would be 97. Our mean, they told us in the problem, is 99. And our standard deviation, they told us in the problem, is 9. So nothing's new. Our calculator does all of the hard work for us, thankfully. Boom, there's our answer. 0.40676, which will round up to 0.4068. So that's the last one that's straightforward. Straightforward as in they just tell us like our mean equals, our standard deviation equals, plug it in. It's the same exact thing for these next examples that are straight from the homework. We just kind of have to read a little bit to figure out our mean and standard deviation and what it's asking for, but it's Still the same thing. So let's go for it. Stop me if you have a question. It says the 50-yard freestyle times of a college swim team are normally distributed with a mean of 26. So notice it says normal, not standard normal. So that's going to give us X values. Our mean of 26, so I'm going to go ahead and write that down, mean of 26. And the standard deviation of 2.43. Determine the probability that a randomly selected swimmer has a 50-yard freestyle time of 22.97 seconds or less. So it's asking for the probability that X, because we're talking about normally distributed, not standard normal, has a freestyle time of 22.97 or less. So 22.97 is bigger or equals to. So X is less than or equal to, thank you. X is less than or equal to 22.97. Round to 4 decimal places as needed. So now it's exactly like every other problem we've been doing. In the middle is our mean, which is 26. Our X value is 22.97, which is smaller, so on the left-hand side. And we're saying X is less than or equal to. So everything's smaller, everything to the left, going on forever towards negative infinity. So our probability, which is our shaded area, just like we've been doing, on our calculator, we're going to do normal CDF. Second vars, normal CDF. Our lower limits on the left-hand side of our shaded area is negative infinity. So we're going to put that into our calculator as negative 99999. Our upper limit is 22.97. Our mean for this problem is 26. And our standard, 22.97. Our mean is 26. And our standard deviation is 2.43. Remember, our mean and our standard deviation, it's not standard normal, it's not Z, so it's not 0 and 1. It gives it to us in the problem. Pressing paste, our calculator should look exactly like it's written. Boom, there's our answer, 0.1062. That's our probability, rounded to 4 decimal places. That's our shaded area. That's our answer, 0.1062. So chapter 6 is all the same thing over and over and over, which is nice. I'm going to keep going for time's sake, but stop me if you have a question, please. The speeds of all pitches thrown by the IRSC softball team are normally distributed with a mean of 67.5 miles per hour. So our mean is 67 miles per hour. Note it says normally distributed, so we know we're dealing with X's. So our mu is 67.5. Our standard deviation of 2 miles. Determine the probability that a randomly selected pitch has a speed of more than 67 miles per hour. So we're looking at our probability of X is more than, so greater than 67 miles an hour. So probability, which is our shaded area, that X is greater than 67. Same thing. In the middle is our mean, which is 67.5. Our X value is just 67, so on the left-hand side of our mean. And we're saying that X is greater than. So our picture really helps us to see our lower boundary and our upper boundary. But it also really helps us to see that, okay, I know that this graph is more than half, so our answer, our probability, our shaded area should be more than 0.5, just by looking at our graph. So on our calculator, normal CDF. Why did I do capital? normal CDF. So in our calculator, second bars, normal CDF. Our lower limit, looking at our left-hand side of our shaded area, is 67. Our upper limit is going on forever to infinity, so I can't plug infinity into my calculator, so I'm going to plug in 99999. It's a handful of nines. Doesn't matter how many, just put in a handful, because we're going to round it anyways. Our mean is 67.5, and our standard deviation is 2. Just make sure you put enough nines in there so that way it's big enough. Pressing paste, our calculator should look exactly like we have it written. Boom, there's our answer. Our probability, our shaded area is 0.59870. So 0.5987 rounded to 4 decimal places. One more for this page. Student loan debt is a growing problem in the U.S. According to Experian, each student borrower owes an average of $30,960. So that average is telling us our mean. That average is telling us our mean. So mean is the average of $30,960. The standard deviation of the amounts all student borrowers owe, so our standard deviation is going to be 2,630. Determine the probability that a randomly selected student borrower owes between $24,341 and $27,076 in student loans. Round to 4 decimal places as needed. So what's the probability that X, because we have a mean and a standard deviation, other than 0 and 1, is between 24,341 and 27,076. I wrote that kind of small. Let me rewrite it. See it better. All right, so drawing this on our graph, in the middle is our mean, which we know is 30,960. And our X value is going to be between 24,341, which is smaller than our means on the left-hand side, and 27,076, which is also smaller than our mean, so also on the left-hand side. So we know they're both going to be on the left-hand side. So we know our shaded area is less than half, so our answer should be less than 0.5. So on our calculator, normal CDF. Our lower limit is 24,341. Our upper limit is 27,076. I don't have enough room. Let me scoot it over. We said our lower limit was 24,341. Our upper limit's that 27,076. Our mean is the 30,960. And our standard deviation is 2,630. Notice that our commas separate each value, our lower, our upper, our mean, our standard deviation. So don't use commas as thousands. Notice I didn't use commas here for my thousand spot. Just type the number straight in. So second bars, normal CDF. Our lower limit is 24,341, no commas. Our upper limit is 27,076, no commas. Our mean is 30,960, no commas. And our standard deviation is 2,630. Pressing paste should look exactly like we have it written on our paper. Pressing enter, there's our answer. 0.06394, So 0.0639 is our final answer. And that's pretty much it. We had 2 more problems on the next page that I got a lot of questions on because they were kind of worded weird. I think that the wording is the weirdest part. So I wanted to go over those next 2, and then we'll talk about something else. Questions on this one? Let's take one more. How you feeling? Boring, because this is the same thing.
I like it. Just typing it in.
Yep, just type it in, and it's kind of like straightforward. Everyone usually likes this chapter.
I don't know about these next ones because I read ahead and like you said, the wording.
The wording is just so weird, and once you see it, you're like, okay, that kind of makes sense. But seeing it once, and remember, I go through every single homework, every single quiz, every single extra credit, every single test problem, and these were the weird ones. So yours will look just like this. So I'm not going to give you something that's weird. Lydia, do you have a question?
Yeah. How do you know the last one?
Uh-huh.
Normally distributed. Like for the others, it specifically said normally distributed.
Because this section's about normally distributed. We haven't talked about one that's not
so
normally.
we get questions that ask for like that would require a Z number.
No, so because I knew this one wasn't a Z value because it told me a standard deviation that wasn't 1 and a mean that wasn't 0. So I knew it was X because if it's Z, mean is 0, standard deviation is 1. But I knew it was still normal, even though it wasn't standard normal, because it's in this section. We're not going to do something that's skewed. In this class. Yeah, like it'll say if it's standard normal, that tells us to use Z, and there won't be a mean and there won't be a standard deviation given because it's understood if it's standard normal, it's understood that mean is 0, standard deviation is 1. Kind of like one, like these, like it didn't tell us a mean and it didn't tell us a standard deviation. It just said that it's standard normal and it gave us a Z value. So that word standard normal tells us to use Z, it tells us that mean is 0, standard deviation is 1. No, because a word problem is more of like a real life scenario. If it's a real life scenario, usually our mean's not going to be 0 and our standard deviation's not 1. But if it was, you could still do it. It would just say standard normal specifically in the problem, and that would automatically tell you Z. So automatically tell you mean is 0, standard deviation is 1, and it wouldn't give you another option for our average or our standard deviation. Thank you for asking. That's a great question. What else? All right, so let's knock out these last 2 that are like this. It says a single serving coffee machine, so a Keurig, is programmed to dispense 12 ounces of coffee per serving. Occasionally, the machine will start to overfill or underfill cups of coffee and require recalibration. According to the company, the coffee machine requires recalibration if it overfills or underfills the cups by 0.5 or more ounces. Determine the probability that a randomly selected cup of coffee was under or overfilled by more than 0.5 ounces. Assume the distribution of the amounts of all coffee dispensed by the machine are normally distributed with a mean of 12 ounces and a standard deviation of 1.45 ounces. So again, it says normally distributed, so it's going to be X. They gave us a mean and a standard deviation, so I automatically know it's not Z anyways. It's asking us to determine the probability. The probability, remember, is our shaded area. And it says, find the probability that the selected cup of coffee was under or overfilled by more than 0.5 ounces. By more than 0.5 ounces. All right, so our picture really helps us here. So in the middle is our mean, which is 12. Right up here, mean is 12, and our standard deviation is 1.45. So if our cup was underfilled by 0.5 ounces, so if I go from our middle of 12, where it's supposed to be, underfilled So it doesn't have 0.5 ounces. That would give us our X value of 11.5. Because we're going down 0.5. It says underfilled by half an ounce. Okay, so it says underfilled by more than 0.5. So if it's 0.5 or more, so that means everything on the right-hand side going on forever towards negative infinity. Likewise, if it's overfilled by more than 0.5, so our boundaries, our other X value of 12.5 now, so we're going below 0.5 and we're going above 0.5, kind of like that word within that we talked about earlier, by 0.5 or more. So or more means everything on the right-hand side going on forever to infinity. All right, this is weird. We haven't done one like this, but what we can do is find the area in the middle, because we're still trying to find the shaded area. We can find the area in the middle like we've been doing, and then find whatever's left over, so find 1 minus. So area in the middle. So finding the area in the middle, just like we've been doing. Ryan, go for it. Yeah, you can totally do that. You can do the left-hand side and the right-hand side, and it should be the same answer in the end. Great question. So normal CDF, second bars, normal CDF. Our lower boundary is 11.5. Oops. Our upper boundary is 12.5. Our mean, they told us, was 12, where it's supposed to be. And our standard deviation, they told us, is 1.45. Pressing paste, pressing enter. So that's the area in the middle, but I don't want the area in the middle. I want the shaded area. So to find the shaded area, we're going to find the whole area we know is 1. The total area is 1. So 1 is a total area. Minus this area in between. So I'm going to write down normal CD, because I don't want to round. Normal CDF of 11.5, comma 12.5, comma 12, comma 1.45. In my calculator, let me show you, because I already put that in. I can do 1 minus and then do my answer. Notice above my negative sign says my answer. So second enter, second negative would give me my 1 minus that answer. So boom, there's what I did. There's your answer. So 0.730224, so 0.732. So you found the area in the middle. Then to find the area on the outside, the shaded area, we had 1 minus answer. That's what gave us 0.7302, which is our overall final answer that we're looking for. I know, that's just weird. Just we were talking about, I should have not said, how are you feeling? But it was the weirdest one. The weirdest one. This next one's not weird. It's just the wording. Ready for another one? So it says the heights of all men in the US are known to be normally distributed with a mean of 69 inches. So I'm going to go and write that down. So our mean is 69. And our standard deviation is 2.8. So mu is 69 and sigma is. Navy requires the fighter pilots to have height between 66 and 88 inches. Here's what's weird about this one. I guess not weird is the answer, but I got a lot of emails because everyone's like, I'm doing it right. And they were doing it right. But this says find the percentage So that word percentage means I have to take my answer as a decimal and then turn it into a percent. So find the percentage of men in the US that meet this height requirement, rounded 2 decimal places if needed. So we're trying to find the probability that their height, so the X values between the 66 and 88. So the probability that 66 is less than X is less than 88. That our X value is between 66 and 88. Same thing like we've been doing. So in the middle is our mean, which is 69. Our X value, which is 66, is less than that 69. Our other X value is greater than that. So on the right-hand side, which is 88, we're trying to find the area between the two. So remember, our probability is our shaded area. So on our calculator, we're still doing the same thing, normal CDF. Second bar's normal CDF. Our lower limit's 66. Our upper limit's 88. Our mean in the middle is 69. And our standard deviation they give us is 2.8. Pressing paste, it should look exactly like we see it on our paper. And our answer is 0.85801, so 0.8580. But just remember, it didn't ask us for the decimal, it asked us for the percentage. So just one more step of moving our decimal 2 places to the right, and that would give us our answer in percentage form, rounding to 2 decimal places, which would give us 85.80%.
You want to change the 86%?
It said 2 decimal places, so 85.80. And I'm glad you said that. So that's why I put the 0, because sometimes people are like, oh, well, I don't need the 0. The 0 shows that I rounded it to 2 decimal places, so put the 0. Other questions? Thank you for asking. So thus far, we've been tasked with finding the probability, which is the area under the curve, when either the Z or the X value was given. I don't know, what was I doing when I was writing this? But we will often need to reverse the process. So that is, we need to find the Z value or the X value whenever they give us the probability or the area. So we're working backwards. So finding the Z-score whenever they give us the probability or the area under the curve. So we can either use the table which is, I'll show you one time, but it's confusing, by looking up the area to the left of the Z value, which is in the middle, and then finding the corresponding Z value, or we can use the inverse norm in our calculator, area to the left, our mean and our standard deviation. If you have a newer 84 calculator, the features are a lot easier. I can plug in left, right, or center. All other calculators, if it doesn't give you the option to plug in left, right, or center, it will automatically give us the area to the left. Just wanted to type that out, but I'll show you. Let's do an example. Determine the Z value such that the area to the left of Z is 0.0028. Round your answer to 2 decimal places. Okay, so it tells us Z. So we're going back to standard normal. So our mean is 0 and our standard deviation is 1. Notice it doesn't tell us a mean or a standard deviation. But because it's Z, we know automatically that it's going to be 0 and 1. It also says the area to the left. So in the middle is our mean, which is 0. And the area to the left is 0.0028, which is really small. So if the area to the left is really small, that means the Z value should be somewhere over here on the left-hand side of our mean. So this is telling us that our Z value should be negative. So this shaded area to the left is really small. That shaded area is 0.0028. So I'm going to show you on the table, one of each. Yeah, I really want to, but
I just didn't know how to use it.
yeah, I'll show you one time, just one time on the table, but normally we're just gonna use a calculator. But I'll show you on the calculator also. So on the table, so in the middle, we know that it's gonna be negative, so we know it's gonna be on this side of our paper, on the negative side. In the middle, we're gonna find 0.0028. It's like a scavenger hunt. 0.0028. Boom, right here. So in the middle, I found 0.0028. This gives me a z-value of negative 2.77. Negative 2.77. So in the middle, we found 0.0028, which corresponds to z equals negative 2.77. Notice it's area to the left, so that helps us too. On our calculator, let me show you how we're all going to do it. Let's be honest. On our calculator. Again, we're going to go to second vars. And then notice down, it says inverse norm. We're doing the opposite. The opposite is the inverse of normal CDF. So inverse norm. Notice it says area. Our shaded area was 0.0028. So that's our area to the left. Our mean is 0 and our standard deviation is 1 because we're talking about z's. And then my calculator gives me the option to do the tail. Is it in the left, right, or center? We have area to the left, so I'm going to put left. If your calculator does not give you that option, it's going to automatically assume it's always to the left, which is fine because we have the area to the left here. Pressing paste, it should look exactly like we see it. Pressing enter, there's our answer. Our z value, no matter which way you did it, was negative 2.77. So we have 2 more pages. To be respectful of your time, if you need to go, you're welcome to go. I'm going to stay recording. So if you can stay here, I'm going to try to knock out these last 2 pages as fast as possible. But if you need to go, you're welcome to go and watch the recording to finish up pages 8 and 9. But like I said, I'm going to stay here and finish wrapping up the last 2 pages, and then we'll leave. So determine the value of z such that the area to the right. So this time we're doing the area to the right of z. So talking about z, so our mean is 0 and our standard deviation is 1. And is 0.0129. Round our answer to 2 decimal places. All right, so in the middle is our mean, which is 0. Notice the area of the right is 0.0, so super, super small. So somewhere over here, the area to the right is super, super small. So 0. Oh, perfect. Thank you so much. See ya. 0.0129. This will tell us that our z value is going to be positive. This will tell us that our z value is going to be positive. So for time's sake, on the table it gets super confusing because the table tells us area to the right. Well, I don't want area to the right. I want area to the left. So I guess we'll just talk about it. So that means the area to the left is going to be 1 minus 0.0129. So this area to the left is 0.9871. 0.9871. So that means on your table, you're going to look in the middle for 0.9871, just like we just did. Find 0.9871 and then look for our z values on the outside. So 0.9871 is right here. This z value would give us 2.23. So 2.23 would be that z value. If you do it in the calculator, we're going to do inverse norm. So second bars, inverse norm. I have the option to do left, right, and center. So if you have the option to do left, right, and center, let's do it that way. So my area to the right is 0.0129. Our mean is 0, and our standard deviation is 1, and that's area to the right. So I'm going to go to right, press enter to highlight right, press paste. It should all look the same. Press enter. Same thing that we just got. Our z value is 2.23. If your calculator doesn't give you the option to do left, right, or center, it's the same thing. So, or inverse norm. You have to use the area to the left. So you have to use a 0.9871, which is the area to the left. Mean is 0, standard deviation is 1. I'll show you. Second bars, normal CDF. Oops, sorry. Second bars, inverse norm. Oops. Second bars, inverse norm. Our area is 0.9871. Mean is 0, standard deviation is 1. And that's if our calculator doesn't give us the option for the tail. If it doesn't give you the option for the tail, it's automatically assumed it's to the left. But either way, you get the same answer. So our z value is 2.229, which will round up to 2.23. I'm just curious, does anyone's calculator not give them the option for left, right, or center? Okay. To be 1000% honest, I'm so used to, like, because this is a newer calculator for me, I still plug it in with the left, even though it gives me the option. All right, let's do the next one. Determine the value of z such that the area between 0 and z is 0.4826 and z is positive. Round the solution to 4 decimal places as z's are traditionally rounded. All right, so in the middle is our mean, which is 0. Our area between 0 and z is 0.4826, and it told us that z is positive. So if z is positive, it's somewhere over here. So between 0 and z, so this area right here is going to be 0.4826. So for everyone, our calculator doesn't give us the option to say, okay, from 0 to z. It just says left, right, or center. So if we all find the area to the left, it's the same thing, because I know this whole area over here is 0.5, because that's half of it. Remember, half of our from our mean, half is 0.5. So everyone's area to the left is going to be 0.5 plus 0.4826. And that would give us 0.9826. So 0.5 plus 0.4826. Oops. Give us 0.9826. So now it's just like the rest of them that we did. Inverse norm. Our area to the left for everyone is 0.9826, comma 0, comma 1, area to the left. By the way, that center is if it's centered with a positive and a negative z value. And it kind of is weird. So to be 1000% honest, I never use the center option. So second bar's inverse norm. Area to the left is 0.9826. Mean is 0, standard deviation 1, and our area is to the left. And this would tell us our z value is 2.110, so 2.11. I'm going to keep rolling. Stop me if you have a question. Determine the value of z such that the area between 0 and z is 0.379. And this time z is negative, rounded 2 decimal places. So in the middle is our mean, which is 0. This time z is negative, so on the left-hand side of our mean. And we're trying to find the area between 0 and z. Or they gave us the area between 0 and z, which is 0.379. 0.379. This one's a little bit tricky. You have two options, but usually we talk about area to the left. So if we're trying to find the area to the left, well, that would give us the area to the right. So instead of adding 0.5, subtract it, exactly. So if we know this whole thing is 0.5, we want to find the area to the left, so we are going to subtract. So 0.5 minus 0.379. If you have a calculator like mine where it gives you the option for left, right, or center, you can do area to the right by adding 0.5 if you would like to. Totally up to you. But it's this half a dozen one way, 6 the other. Doesn't really matter. So 0.5 minus 0.379 would give us 0.121. So that means this area to the left is 0.121. So inverse norm. Our area to the left is 0.121. Our mean is 0. Standard deviation is 1. Again, that's area to the left. Second bar's inverse norm. 0.121 is our area. Our mean is 0. Our standard deviation is 1. Our area is to the left. Pressing enter. Boom. There's our z value. We knew it was going to be negative, so we know we did it right. Z equals negative 1.710. So our z value is negative 1.17. All right, so those are the normal, straightforward ones. Here's the ones that are like, okay, they give us weird wording and they want to throw us off right when we're feeling comfortable. Yeah. So the next one says, stop me if you have a question. Determine the two values of z such that the middle 10% of the data lie between the two z values. Round the solution to 2 decimal places as these are traditionally rounded. All right, so a couple things. In the middle is our mean, which is 0, and it tells us that lie between 2 z values. Everything's symmetric, so it's going to be the same z values. One's positive, one's negative. So this would give us the negative z and the positive z. Negative z is to the left, and the positive z is to the right. In the middle, so we're going to have our shaded area in the middle. And it told us the middle 10%. So this is going to be in the middle 10%, which is 0.10. All right, remember, we want the I'll show you both ways. So let's talk about area to the left. So the area to the left here, this is our unshaded area. So area to the left. Before we do area to the left, let's do, because I can't just find this one. I know the whole thing's one, right? So we're gonna first find our unshaded area. Our unshaded area. So if we know the whole thing's 1 minus our shaded area, which is 0.10, would give us 0.90. But that 0.90 is split up into 2 symmetric pieces. So divide by 2. So that means this is going to be 0.90 divided by 2, which is 0.45. This is going to be 0.90 divided by 2, which is going to be 0.45. It'll all give me 1. Sorry, it's a group chat, but I'm scared to turn my volume off in case someone has a net because they're still on Blackboard. All right, so area to the left. $0.45. Now it's just like the previous problem. So we're going to do inverse norm. Area to the left is 0.45. Our mean is 0. Standard deviation is 1. That's area to the left. Or if you have a calculator like mine where you have the option for, let's do that first. Let me pause. Second bars, inverse norm, 0.45, 0 and 1, area to the left, pressing paste, pressing enter. We get negative 0.1256, which will round up to negative 0.13. So if that's negative 0.13, this is going to be positive 0.13. And that's it. If you have a newer calculator like mine where it gives you the option for center, because we're looking at the center of these 2 symmetric values, you can use that option if you want to. So second bars, inverse norm. Our area is going to be in the middle, 0.10. That's our area in the center. Our mean is 0, standard deviation is still 1, and that's area of the center. Pressing paste. It gives you the same thing. It gives you both of them. Negative 0.125, which is negative 0.13, and positive 0.13. So in between Z is negative 0.13 and positive 0.13. It's the same numbers because of symmetry, because they're symmetric. It's symmetric. So same number. One's positive, one's negative. Positive and negative. Lord have mercy, can you stop? Questions on that one? All right. 4 more examples in general. 3 more are like this where they're just the same thing, just worded weird. Let X be a normally distributed continuous random variable with a mean of 59. So it told us the mean. And a standard deviation of 7.5. Determine the value of X such that the area to the left of X is 0.5517. This is kind of nice. Just like normal. Let me see if I could. Okay. So in the middle is our mean, which is 59. The area to the left is bigger than 0.5. It's 0.5517. So it's more than half. So I know it's going to be to the right of our mean. So our x value we know is going to be positive. Or I shouldn't say something positive. I should say our x value is going to be bigger than 59. The reason why this one's weird is because notice I have a mean and I have a standard deviation. So we're using x. It's not standard normal anymore. We're going to use x, but same thing. And area to the left is 0.5517. So in our calculator, we're going to do inverse norm. My hand is cramping. Area to the left is 0.5517. Our mean is 59, and our standard deviation is 7.5. Again, that's area to the left. So area to the left, our mean, and our standard deviation. So again, our calculator is worth every penny because it does all of the standardization, all that good stuff for us. So second bars, inverse norm. Our area is 0.5517. Our mean is 59. Our standard deviation is 7.5. And we're looking at area to the left. Enter. There's our answer. So now our x value, not z, it's our x because it's not, our mean's not 0 and our standard deviation is not 1. 59.974. So 59.97. One more page. One more page. Questions on this one before we go to our last page. 3 examples and we're done. All right, last page. It says an honor society on campus only accepts the top 11% of students according to GPA. If the GPAs of all students on campus are known to be normally distributed with a mean of 2.93 and a standard deviation of 0.38, determine the minimum GPA that a student must achieve in order to be admitted into the honor society. Again, same thing we've been doing, it just words it weird. So a couple things, it tells us the mean is 2.93 and the standard deviation is 0.38. And it tells us it only accepts the top 11%. So the top 11%. So our right tail is going to be 11% or 0.11. In the middle is our mean, which is 2.93. And this is our x value. So we're looking for that x value. Notice this x value would give us the minimum needed. This would give us the minimum needed because we're looking at it from left to right. So because it's on the right hand side, this is the minimum, so we're good. All right, so 2 options. If you have a calculator like mine, you can do inverse norm. Our area to the right is 0.11. Our mean is 2.93. Our standard deviation 0.38, and that's area to the right. Or if you don't have the option for left, right, center, we just find the area to the left. So we know the area to the left is going to be 1 minus 0.11, which is 0.89. So this would give us 0.89. So, or inverse norm, the area to the left would be 0.89. Our mean is still 2.93. Our standard deviation is still 0.38. And this would be area to the left. Either way, they're both going to give us the same answer. So second bars, inverse norm. I'll start off with both of them. So the first one is our area to the right is 0.11. Our mean is 2.93. Our standard deviation 0.38. And that's going to be our right tail. So going to right and highlighting right, pressing paste, pressing answer. There's our answer, 3.396, which would give us 3.40. Same thing, if you have a calculator, it doesn't give you the option for right tail. Second bar's inverse norm, using the area to the left, which would be 0.89. Our mean is still 2.93. Our standard deviation is still 0.38, and this would be our area to the left. It gives us the same answer, 3.396, which would give us our minimum GPA of 3.40. So our X value would be 3.40. One more weird one like this. I thought the top 11% was kind of a weird wording. So one more weird wording, and then we'll do our last example. So the SAT college entrance test scores are known to be normally distributed with a mean of 1071 and a standard deviation of 95. Determine the 80th percentile of all SAT scores. Okay, like what the heck is that saying? Remember, 80th percentile means it's going to be 80% or lower. 80th percentile means 80% or lower. So let me show you on the picture what on the graph what it'll look like. So in the middle is our mean, which is 1071. 80% or lower. So 80% is most of my graph. So like somewhere over here would be our X value, or lower. So everything on the right hand side. So instead of the top 11% that looked at the area to the right tail, now we're looking at the lower 80%, which would be our left tail. So this is going to be 80%, which is 0.80. So our area to the left is 0.80. So now we're good to go. Inverse norm. Area to the left is 0.80. Our mean is 1071. Our standard deviation is 95. And we're talking about area to the left. Second bar's inverse norm. Area is 0.80. Our mean is 1071. Our standard deviation is 95. Area to the left. So we should all have it in the same no matter what calculator you have. Boom, there's our answer. Round the solution to the nearest whole number. So 1150.95 rounds up to 1151. So our X value would be 1151. One more thing that we need to talk about. That's not the greatest. Then we're done. Sorry. Just wanted to be honest.
Not the greatest.
Let's just get it over with. Okay, questions on this before we do the next one? Last one. All right, converting from a z-score to an X value now. So going from an opposite, because before we did X to Z, now we're going to do Z to X. So if we took our z-score formula and we use algebra to solve for X, we would get that X equals our mean plus our mu plus Z times our standard deviation. Mu plus Z times our standard deviation. This formula is on your formula sheet, so don't worry about using algebra to solve it. It gives both of those formulas to you. All right, so this formula takes a z-score whenever our mean and standard deviation are known, measures in standard deviation, and it converts it back to the original units of X, which is in dollars, pounds, or whatever the problem is going to be. So again, going from Z back to X. So a soft drink machine at a local fast food restaurant can be calibrated so it dispenses an average of mu ounces per cup. If the ounces of sodas dispensed are normally distributed with a standard deviation of 1.4, find the value of mu. So we don't know mu, we're looking for mu. So we don't know mu, we're looking for mu. They told us our mean. They told us our standard deviation is 1.4. So find the value of mu such that a 24-ounce cup will overflow only 10% of the time. So overflow only 10% of the time. So overflow is going to tell us that it's going to be more than we want. So to the right. Rounded solution to 1 decimal place. All right. So it also tells us that a 24-ounce cup will overflow 10% of the time. So this is telling us how many ounces we're looking for. So this is telling us our X value is 24. Our X value is 24. All right, so we're looking for our mu. Doesn't matter what formula really, because we're gonna use either one, but let's use this one. So if we have X equals mu plus Z times our standard deviation, we have X, we need mu, we also need Z, and we have our standard deviation. So let's use this, we need to find mu, but let's use this to find Z. So in the middle is our mu, we don't know what it is, but we know it's our mu. And it says it's going to overflow 10% of the time. So our right tail, area to the right, is going to be 10%, which is 0.10. That means our area to the left is 1 minus 0.10, which is 0.90. So just like we've been doing, so our Z value is going to be inverse norm. They give us the area to the right, so I'm going to do it both ways. So I have the option of area to the right, so my area to the right is 0.10. We're talking about Z, so for Z, because we're looking for our Z value, our Z has a mu of 0 and a standard deviation of 1. And that's going to be area to the right. Or you have the option if you don't have left and right and center. Inverse norm, our area to the left is 0.90, comma 0, comma 1. And this will give us our Z value. So either way you do it. So second bars, inverse norm. If I have the option of the right, my area is 0.10, mu is 0, standard deviation is 1, area to the right. Same thing if you have second bars. If you don't have the option for the right, I can plug in 0.90 for my area, 0 and 1, and that's area to the left. Notice it gives me the same answer. It gives me the same answer. So my Z value, I don't want to round it because I don't want to round it to the very end. Be careful. If you round it here, it's going to round your X value because remember our answer is going to be X. This isn't our answer. This is just Z. So Z is 1.281551567. All right, so now that we have our Z value, we can plug it into this formula to find our mu, to find our mean. So X equals mu plus Z times our standard deviation. Our X value they gave us in the problem was 24. Our mean, we don't know our mean. We're looking for our means. We're going to solve for our mu. Plus our Z value, which we just found, which was 1.281551567. And our standard deviation they told us was 1.4. So getting our mean by itself, I can subtract this 1.281551567 times 1.4 on both sides. 15515. That way those cancel. So our mean is going to be 24 minus 1.281551567 times 1.4. In my calculator, notice I don't have to write that whole thing because I already have it in my calculator. I can do times 1.4 equals, and I can do 24 minus that answer. So 24 minus, remember answer is second and then your negative sign. So 24 minus that answer, boom, there's my mean. And it said round to 1 decimal place. So 22.20 will round to 22.2 ounces. So I felt like it's just going around a long way to get to the answer. But we did it. We did it. So questions, comments, concerns, how could I help you with chapter 6? Chapter 6. If not, thank you so much for staying. Thank you for watching the recording. If you have any questions, please let me know. Please let Delaney know or the ASC lab know. If not, have a great week, and I will see you. Remember to do chapter 6 homework. I will see you next week for chapter 7. Bring your chapter 7 notes packet. Thank you.